Chapter 4, Section 4, Exponential and Logarithmic Equations. So here starts our process of solving exponential and logarithmic equations. An exponential equation is an equation containing a variable and an exponent. We already saw that, like f of x equals 2 to the power of x. We use natural logarithms to solve exponential equations. You'll see how this works, right? Because logs are exponents, and it's the inverse of the exponential, so it makes sense, right? When we are taking the square root of something, it's to do the inverse of squaring. When we're subtracting something, it's to do the inverse of adding. Equation solving is all about inverses. So if we're solving an exponential equation, it would make sense that we are going to use logarithms to do it. It makes sense to me anyway. Isolate the exponential expression. Okay? Anything in front of it or behind it, gotta go. You gotta get that exponential expression isolated. Folks, it could be a single item or it could be a quantity. All right. Take the natural logarithm on both sides of the equation. Okay, whatever you do to one side, you do to the other. It's got to be both sides. Number 3, you're going to simplify using one of the following properties. Natural log of b to the x equals x times the natural log of b. Right? That's your power rule. Or natural log of e to the x equals x. That's your inverse property. All right? So this one here is power rule. And here, this is inverse property. And then finally, solve for the variable. Now, these are equations. You're going to get solutions, so you need to use set notation. Keep that in mind. All right, let's look at our first example, which is checkpoint number 1. Solve 5 raised to the power of x equals 134. Okay, so when I'm solving exponential functions, and I know this is a little silly, just bear with me. It is what it is. This is my algebra land brain story. Okay, this thing here is up high on a shelf. I can't reach it. I need to get it off the shelf. Who are you going to call for help? You're going to call Lynn. Hey, Lynn, can you help me out? Lynn says, sure, I'll help you out. But if Lynn comes to the rescue on the left side, she also comes to the rescue on the right side. Okay? Take the natural log of both sides so that you can use the power rule that allows the exponent to come out front. On the left side, I have x times the natural log of 5 equals the natural log of 134. The only way to break this apart is to divide. Folks, the natural log of 5, you can't just divide by 5. This thing is a package deal. It's a natural log of 5, log base e of 5, okay? So we're going to divide both sides by ln 5. So we get natural log of 134 over the natural log of 5. Now, of course, if this was an application problem, you would have to get a decimal approximation in order to answer the question. But this is not an application problem. So my answer in set notation is the exact natural log of 134 divided by the natural log of 5. You can't divide lns out, okay? They stay. This is a number, that's a number by itself. If this was an application problem and you had to get the actual physical number so that you could use it to answer the question in terms of whatever's being asked, then we would get the calculator and type in the natural log of 134. Notice the calculator opens a parenthesis. You need to close it. Divided by the natural log of 5 closed. I got 3.04319897.2. We're going to round to 2 places here. Again, you only do this if you need to answer an application problem. All right, this is the solution in set notation. This is the approximation used for application problems. Or if the directions tell you to round to the nearest whatever place. Okay. So let's see the next one, next example. 7 times e raised to the 2x power equals 63. This one's a little bit different than this one because here the base raised to the power of x was already isolated. This one is not. You have to get rid of this 7. It's a nuisance. The only way to get rid of it is to divide. Okay, so let's divide. E to the 2x equals, divide by 7, that's going to make that be a 1, right? And 63 divided by 7 is 9. All right, what do we got? Well, oh, it's up there, up high on the shelf. Who are you going to call? Lynn. And we want Lynn each time. Log would work, but then I can't use the inverse property if I'm using just log base 10. That's why it's just easier to remember Lynn. Who are you going to call for help? Lynn. I mean, what I'm saying is log would work up here because we know natural log of 134 divided by the natural log of 5 is going to be the same as log of 134 divided by log of 5 for the previous problem up here. But sometimes you have base e, so it's just easier to use Lynn all the time. Okay, so natural log of e to the 2x equals natural log of 9. What are you going to use next? Well, you could use power rule, or what's the natural log of e to the 2x power? That's the inverse property that we saw up here. Yes? Natural log of e to the x equals x. Natural log of e to the equals that. So it's 2x. But you could use the power rule, put the 2x out here, and then you would have to know that the natural log of e is 1, so that would be 2x times 1. Or why don't you just go right to 2x? Equals the natural log of 9. X is still not by itself. I'm going to divide by 2. X equals the natural log of 9 divided by 2. If I am doing an application problem and want to get a decimal approximation, go to my calculator. Natural log of 9 divided by 2 is about 1.10 if I'm going to 2 places. However, the exact answer is set notation, natural log of 9 over 2. Okay, so if you have any questions on that, please ask. I will help you if you ask. I won't know to help you if you don't ask. All right, let's see what is on page 2 of these notes. Oh, there's 2 examples on this page. Solve. Let's give the problem. Remember, the problems are the checkpoint examples. This is 6 raised to the power 3x minus 4. Subtract 7 equals 2081. You have to isolate the exponential expression. That's this piece right here, which means we have to get rid of the 7. Do inverse operations. That's what solving equations is all about, breaking it down, doing the reverse, taking it apart. The left side is 3 raised to the 3x minus 4 power. Add 7, this side becomes 2088. I've got it up there, up top in this shelf. It's up there. It's like, hey, Lynn, come and help me. So I got the natural log of 6 to the 3x minus 4. Now, here's where sometimes students get goofed up. When they use the power rule, folks, this is a quantity and it must be grouped. It's a quantity and it must be grouped. So when you use the power rule, I get quantity 3x minus 4 times the natural log of 6 equals the natural log of 2088. I've got a grouping with x in it. I have to solve for x. You have to distribute. This is 3x natural log 6. Subtract 4 times the natural log of 6 equals the natural log of 2088. I have to solve for x, which means I need to get rid of this by addition. 3x natural log of 6 equals natural log of 2088. Add 4 times the natural log of 6. Divide. Folks, we want x by itself. We're not going to divide and then divide again. We're going to divide in one fell swoop, which means we're going to divide by 3 times the natural log of 6. Folks, multiplication is commutative. 3 times x times ln 6 is the same as x times 3 times ln 6. Okay, so I'm dividing both sides by 3 times ln 6. The numerator is the natural log of 2088 plus 4 times the natural log of 6. This is a quantity divided by 3 ln 6. You can't switch the 6 and the 3, right? It's the natural log of 6. It's 3 times the natural log of 6. Technically, 3 is the exponent, right, on 6 if I would use the power rule. We don't need to do that here, but that's what it means. So this is my final answer, which I put in set notation. This is my exact answer. Natural log of 2088 plus 4 times the natural log of 6 divided by 3 times the natural log of 6. That's exact answer. Now, you need to watch your parentheses here, and please practice this. I'm going to group this on my calculator. Natural log 2088. Calculator, open a parenthesis. I need to close it. Plus 4 ln 6. Close. Close. This second parenthesis is closing that first. Divided by. Folks, you need parentheses here. You have to tell the calculator to divide it by this product. So use the parentheses. Parenthesis 3 ln 6. Close, close. 2.755392131. Or about 2.76. Folks, remember, you're only giving this answer if you're using an application problem, or if you're asked to round to the nearest hundredth. All right, let's take a look at this and see what happens if I didn't put that in parentheses. So I'm going to do a second entry to call it back up. And I'm going to delete that parenthesis. And I'm going to delete that one. See, I get a different answer. You need to group that denominator product, especially if you're using the 84. Not really quite sure. The color addition might... No, the color addition is not going to open up a parenthesis for the divided by. I don't think it does. So be cognizant of how you have to type this in, because if not, you're going to get the wrong answer. All right, if you've got questions on that, please reach out so I can help you. Moving on to the next example. Solve. These are fun ones. All right, I've got e to the 2x power. Subtract 8 times e to the x power plus 7 equals 0. It's a trinomial. You have to factor the trinomial. Well, the leading coefficient is 1. It's quadratic in form, right? E squared. Try it. Leading coefficient is 1. That's a 7. Multiplies to 7, adds to 8. Well, that's not too bad. That's 1 and 7. Do you remember when we did t substitution? It's kind of similar, right? So here we got e to the x, why e to the x? Because e to the x times e to the x is e to the x plus x, or 2x. We got a 1 here, we got a 7 here, signs are the same, they're both minus. Check it. That's e to the 2x, that's minus 7 e to the x, minus 1 e to the x is that middle term. Negative 1 times negative 7 is positive 7. It works. Now we split, we use ZPP. E to the x minus 1 equals 0. E to the x minus 7 equals 0. Take the 1 over. Because remember, you have to isolate the exponential item in your equation. I'm going to work this side as well. It's up there on the top shelf called ln for help. Ln e to the x equals ln 1. Ln e to the x equals ln 7. Use the inverse property. Natural log of e to the x equals x. So x is equal to the natural log of 1. Use the inverse property here. X is equal to the natural log of 7. Natural log of 1. I'm not going to leave it like that. This is one of our common properties. Yes, log base e of 1 is 0. Right? Because e to the power 0 equals 1. And over here, well, not much I could do about this. If I wanted to get a decimal approximation, we know we could just type in natural log of 7 and get about 1.95. But again, this is for application problems. Our solutions are 0 and natural log of 7 as our exact answers. Okay, hopefully you are finding that this isn't too terribly terrible and that this is doable and that you might actually enjoy it because it's something different. Okay, so remember when it's a trinomial, you have to factor and then use ZPP, right? Factor and use ZPP. And then you're going to use call in for help. All right, page 3. Now we're going to look at how to solve equations that are logarithmic. These other ones were all exponential. But the log equation is the inverse of the exponential. So a logarithmic equation is an equation containing a variable in a logarithmic expression. If a logarithmic equation is in the form log base b of x equals c, we can solve the equation by rewriting it in its equivalent exponential form. B, right, b to the c equals x. Let's see how this works. Solve log base 2 of x minus 4 equaling 3. It's in log form. I only see the word log one time. I can convert it because I know what the base is. The base is 2. I know what the exponent is. The exponent is 3. This becomes 2 cubed equals x minus 4. 2 cubed is 8, and I like my x on the other side. So I'm just going to simply rewrite x minus 4 over here, and I'm going to cube the 2 and get an 8. When I add 4 to both sides, I see x is 12. I'm going to check it, right? Because this thing here can't be negative. So you got to check these. You must check these. So I got log base 2 of 12 minus 4 equals 3. Well, 12 minus 4 is 8. Log base 2 of 8. Is that 3? Well, yeah, because 3 equals 3. Then and only then can I put my solution in set notation. Remember to put the solution in set notation and not the check value. Okay, you must check. You have to, because if this thing ends up negative, it's kind of like those box problems we had. You couldn't have negative side length, okay? 2 to any power is never going to give me a negative number. This has got to be a positive number. So you got to check it. All right, one more example. This one will, I mean, it's not long, but it's a little bit long. Using the product rule to solve a log equation. So we're going to solve log of x plus log of x minus 3 equals 1. Folks, I see the word log twice. I can only see it one time. So I have to use those properties of logarithms to condense so that I can then convert this into its equivalent exponential form. All right? The addition means multiply these things. That's why we did that condensing and expanding. All right, so this becomes log, and remember, this is base 10. This is log of x multiplied with x minus 3 equals 1. Now, keep in mind, I'm solving this for x, so you are going to have to multiply this. All right, let's see what this is going to look like. I'm going to convert it to exponential. My base is 10, right? So this is 10 to the power of 1 equals this product. Now I'm going to multiply this out. I'm going to move it to the left side because I like my x's on the left side. X times x is x squared. X times negative 3 is negative 3x equals 10 to the power of 1 is 10. It's quadratic. I have quadratic, linear, and constant. Move the constant to the other side. X squared minus 3x minus 10 equals 0. Factor multiplies to 10, subtracts to 3. Well, that's going to be 5 and 2. Larger product has to be minus, so 5 gets the minus, 2 gets the plus. ZPP says x is equal to negative 2 and x is equal to 5. Those are my proposed solutions. I have to check these. All right, let's see if I have enough room to write here for my check. You must check. It's not optional because you're going to get wrong answers if you don't. All right. Log of x plus log of x minus 3 equals 1. All right. Negative 2 is my first value that I'm checking. Folks, 10 to what power gives me negative 2? It's never going to happen. Okay? Negative numbers do not have logarithms. So if you end up with something negative here, it's not possible. Negative numbers do not have logarithms or logs. Okay? And it's because, like, 10 to what power gives negative 2. I don't think that's ever going to happen. Let's type it in the calculator and see what happens. Log negative 2. Ah, non-real answer. Doesn't exist. Okay, so can't be negative. It's because of that. This one too, right? Can't be negative. All right, let's check the second solution. So we know this is an extraneous solution. All right, check. Log. I like the parenthesis for x plus log. Parenthesis for x minus 3. Close equals 1. Substitute my value in, this time of 5. This becomes log of 5 plus log of 5 minus 3 is 2. You can put this on the calculator, or look, I could put this back together by multiplication. Log of 5 plus log of 2 is really log of 5 times 2, or 10. Log of 10 is 1. So that works. And now I conclude that my solution is 5 and only 5. Okay, because the negative 2 was extraneous. You know, we could check this on the calculator. Clear log 5 plus log 2. It's quicker to not do it on the calculator. There it is. It equals 1. Log of 5 plus log of 2 equals 1. Okay. So, if you have questions, please let me know. You will be working on an assignment. And please, please, please check your answers in the back of the book. Even if you're doing the checks, check your answers in the back of the book. I can't stress this upon you enough. Okay, reach out if you need to. Have a great day.